Welcome back, everyone. In this video, we're going to be looking at some of the ideas of Isaac Newton and how they fit into the overall philosophical picture that was developed around the time in the very late modern period. So in this video, we're going to talk about Newton's three laws of motion just very briefly, but then we'll talk about how it relates to this idea of mathematical philosophy and experimental philosophy. And that includes some discussions of questions that people had about Newton's theory of gravitational force, about Newton's empiricism and the way that he thought about the purpose of science or the purpose of experimental philosophy, and then two different possible interpretations of Newton's view about the nature of science. So Newton's three laws of motion are introduced in this reading for this week. The first law of motion essentially says that an object in motion tends to stay in motion, and an object at rest tends to stay at rest. So something will continue moving the way that it is, in the direction that it is, unless some other outside force acts upon it. And we'll see this idea of force is really important to Newton. So you can find this page 313. He says, every body preserves in its state of rest or of uniform motion in a right line, unless it is compelled to change that state by forces impressed thereon. Then we get his second law of motion, which says that force is equal to the mass of the object multiplied by acceleration. As he says, page 313, he says the alteration of motion is ever proportional to the motive force impressed, and is made in the direction of the right line in which that force is impressed. So the idea here is that the way in which some object's motion is changed is going to be mathematically proportional to the force that acts upon that object in relation to its mass. And then the ellipsis there is because if you read the rest of this law, you'll see it filled out. And then the third law of motion says that for every action, there is an opposite and equal reaction. Now, the way this is actually put in the reading is he says, to every action there is always opposed an equal reaction, or the mutual actions of two bodies upon each other are always equal and directed to contrary parts. And so an example here is this idea of if I push against the wall as hard as I can, I am exerting a force. I'm exerting pressure onto the wall. I'm pushing against the wall. But in a sense, there's a force that the wall is also exerting on me, that force of resistance, essentially. And the force of resistance that it acts upon me is equal to the force that I act upon it. Now, this is pretty important to Newton's overall ideas of force within his physics. Now, we're not going to go through the details of the mathematical elaboration that Newton does of these three laws, but I just want you to notice some of these general features. We have this appeal to force. We have this appeal to some outside force acting upon something. We have this idea of being able to describe one action, pushing against the wall, in two different ways. The force being pressed upon the wall by me and the force that it's exerting in return. We also have this description of the behavior of objects, their motion, being mathematically proportional to other features of it. So Newton explains changes in motion by appealing to that idea of force being exerted on a physical object. But what are these forces? So let's consider an example. I'm playing baseball with my son, and I throw a ball. My son swings a baseball bat and hits the ball. So at that point, the baseball bat exerts a force on the ball, and now the ball starts moving in the other direction. And those changes in the motion of the ball obey Newton's three laws, utilizing this concept of force. So the amount of force that the baseball bat exerts on the ball is equal to the mass of the ball multiplied by its acceleration that we observe when the baseball bat hits it and it starts moving in the other direction. Now, this is very different than Descartes' idea of transfer of motion. It isn't that the motion in the bat is transferred from the bat to the ball. Rather, the baseball bat is moving, and because it's moving, when it hits the ball, it exerts a force, and it's the force that then gets the ball to move according to these three laws of motion. So that force that's exerted on the baseball, it's not a feature of my son. It's not, my son doesn't have that force. The baseball bat doesn't have that force, and the baseball doesn't have that force. And we know this because Newton says that the force that's exerted on the baseball doesn't remain beyond the time of the action itself. So the force exists at that moment when you hit the baseball, and then it gets the baseball to move away. But it's not like the force then stays with the baseball and keeps moving with it. No, the force doesn't belong to any of these objects. So forces are not themselves substances. Forces aren't individual things. They aren't independent things. They depend upon the actions of other things. But they're also not modes of substances, because the force is not a feature that belongs to any of these physical objects either. It looks like this force is some extra thing in the world. So what exactly is it? Now, Newton seems to suggest, and he's unclear about this, and it caused a lot of confusion at his time with people reading Newton, but it looks like one way to understand this is that Newton sees a force as a measurable quantity. Notice the idea of forces being proportional to one another in Newton's three laws. This idea of being proportional is a mathematical description of what this force is. So the force is just whatever it is that's picked out by this mathematical equation. It's just this quantity we can describe and measure. Now, this also makes Newton's theory of motion and gravity very different than a purely mechanical explanation. Now, this is even more obvious when you consider Newton's ideas on gravity, which we'll consider in just a bit. All right, so some important features of Newton's approach to physical explanation. The behavior of physical objects need to be explained by appeal to some more general physical laws that govern the behavior of all physical objects. So, when the baseball hits the bat, you don't just say the baseball moved because the bat hit it. No, there's some deeper, further explanation about a law of nature that all objects, not just this baseball, not just this bat, are going to behave. There's the F equals ma equation. There's these three laws of motion, and this is the law of nature that exists in the world, and it governs the behavior of all physical objects. And so the reason, the explanation for why the baseball bat moves the baseball in that direction is because there is this law of motion. Now notice though, this raises a question of, well, what exactly are these physical laws, first of all? And secondly, how do we discover or come to know what the physical laws are? Now Newton has a lot to say about how we come to know these physical laws. He doesn't have a lot to say about what the nature of the laws themselves are, like what is a law of nature. And that was actually a really big thing in philosophy after Newton, as we'll see when we look at David Hume. So, the behavior of a physical object and these laws of nature are also described in mathematical terms. These forces are described as quantities. All right, and this is very important. In order to describe these physical laws, they have to be described in mathematical terms in order to make them precise and to give us explanation of what's going on in the world. Now, Newton uses the same approach to develop a theory of gravitational force that can act on these physical objects and explain their behavior. So remember, objects in motion will tend to stay in motion unless some outside force acts upon them. Well, one of the forces that can act upon these objects to change the direction or speed, etc., its motion, is gravitational force. We're not going to go through the details of his theory of gravity, but Newton's thinking led him to a theory of universal gravity. The idea here was that all objects in the universe attract each other with a force of gravitational attraction, according to what's referred to as Newton's inverse square law. We're not going to go through the details of what that inverse square law is. The important part here is that it's described mathematically. There's also this idea of proportion, and this gravitational force applies to everything equally throughout the universe, both on Earth and both in the celestial sphere, so outer space essentially. So the idea of this is that the Earth exerts a gravitational force on the moon in a way that's proportional to the mass of both the Earth and the moon and the distance between them. So those are the things that are going to be mathematically described and give us a result of how much, the quantity of force that's exerted on the moon by the Earth. But this also goes the other way. Just like that third law of motion, we can describe that force in the opposite way, where the moon also exerts a gravitational force on the Earth, equal to its mass and this distance, etc. So in this way, Newton was able to give a unified picture of forces that applied both on Earth and in the heavens, or for the planetary orbits. This was very strange to Newton's contemporaries because they thought of the objects on Earth as obeying one set of laws, but in the heavens, they thought of the planet's motions being described by alternative forces in alternative ways. But according to Newton, the centripetal force that keeps planets in their orbit around the sun is the very same force as the gravitational force that makes objects on Earth fall towards Earth. So there's a kind of unified picture of how everything behaves. Everything in the universe follows these same laws of motion and laws of gravity. But how do we discover what those general physical laws are, such as those three laws of motion or that inverse square law of gravity? He says, in this philosophy, particular propositions are inferred from the phenomena, and afterwards rendered general by induction. Thus it was that the impenetrability, the mobility, and the impulsive force of bodies, and the laws of motion and gravitation were discovered. So notice these two central tools. There's observation, which provides us with our foundational beliefs about specific things that happen. I see this apple fall at this speed at this time. I use my observation to notice that particular phenomena. But then I use induction to extend that belief to how things will behave beyond what I've already observed. Now, both aspects of this philosophy regarding how we gain knowledge of the physical world are diametrically opposed to this rationalist approach we saw in Descartes. This is very much an empiricist approach. So notice that the starting point for learning about the behavior of physical objects is observation, which comes from our senses. But this is very different because, according to Descartes, our beliefs about the physical behavior of objects must come from understanding their essential nature and getting that understanding via our reason. Merely observing their behavior with our senses is insufficient for backing up those beliefs because our observations doesn't tell us about the inner essential nature. Remember that wax passage. We need to get to the essence of the physical object in order to explain how that physical object is going to behave, the laws that it's going to operate by. So there's a big disagreement here between Descartes' method and Newton's method. Now, Newton then also allows us to use induction to generalize our beliefs to these laws of physical objects. So we say, well, this first object, we observed it to behave in a certain way that we can describe with these three laws of motion. Well, a second object, we observed to behave in a way that is also describable by these three laws of motions. Then we do this for a third object, a fourth object, a fifth object. We use our observations to see all these cases. And then we use that to generalize and say, so probably all objects' behavior, even those we haven't yet observed. So the orbits of the planet that we haven't observed directly, that we haven't seen for ourselves, in the future will also obey these three laws of motion. Anything I run into, even if I haven't observed it yet, according to these laws of motion, will obey this behavior as well. Now, Descartes, however, only allowed us to extend our foundational knowledge using deduction. According to Descartes, knowledge requires removing all possible doubt. But induction can't remove all possible doubt, and so it can't give us certain knowledge. Because even if objects have always behaved some way in the past, we could still imagine that they have some inner nature hidden from observation, where that inner nature will cause them to behave differently in the future. And so Descartes thought knowledge of scientific laws about how physical objects are going to behave requires us not to use our senses, because our senses aren't going to guarantee that these objects are going to continue to behave in these ways in the future. So we have to use our reason to first come to know what the inner nature of these physical objects are, and then use our object of its essence to thereby deduce that they're going to behave according to certain laws. So the only way we know we can know that they're going to behave this way in the future is by deducing it from that inner nature that will give us that guarantee. Our observations, if we try to generalize, we might be led astray, since it doesn't tell us the underlying essence that would lead it to behave in that way. So many readers during Newton's time found his views about force and gravity in particular to be mysterious for a couple reasons. So Newton's conception of force didn't look like it fit nicely into a picture of substances and modes of substances. So a force wasn't its own independent thing. I can't understand force without physical objects. It depends upon. If there were no physical objects, there would be no forces. But the force, as we saw, doesn't belong to the baseball bat, doesn't belong to the ball. So what is this force? Is it a physical entity? I mean, a force definitely isn't a material object. So what's being described by Newton's mathematical formula? I mean, we have a description of how forces affect things, but we don't have a description of what the force itself is. Another reason it was mysterious is because Newton's theory of gravity seemed to allow for what his contemporaries saw as spooky action at a distance. So the idea here is that Newton's theory allows us to give a mathematical formula to quantify gravitational force and to make predictions about how physical objects are going to move. However, it doesn't tell us what the underlying nature of gravity is, so as to explain why this force behaved this way. So why does gravitational force obey the inverse square law rather than an inverse cube law, for instance? So here we see Newton say, he says, "But hitherto I have not been able to discover the cause of those properties of gravity from phenomena, and I frame no hypotheses." So he says, when I go try to find out why gravitational force obeys this inverse square law, he says, I can't find any explanation. So he says, I don't give you any. For whatever is not deduced from the phenomena is to be called a hypothesis, and hypotheses, whether metaphysical or physical, whether of occult qualities or mechanical, have no place in experimental philosophy. And to us it is enough that gravity does really exist and act according to the laws which we have explained, and abundantly serves to account for all the motions of the celestial bodies and of our sea. So Newton is taking this very empiricist approach to our knowledge of gravitation. All human knowledge must ultimately be justified by sense experience. Now we can use experiment to extend our observations and we can use mathematics to describe our observations and to try to generalize them to cases we haven't observed. But insofar as there's some claim that we cannot observe or experiment or get at via experiment, then he says we just can't know about it. So the inner nature of gravitation, he says, I've tried to probe it, I've tried to do experiments to find it, but I can't find any deeper explanation. I haven't been able to make those observations, and so I just have no hypothesis. Now, there's two ways to interpret Newton's idea. One is a kind of brute fact interpretation, and this says that these laws of motion and of gravity, since we can observe them, we can quantify them, and we can sort of see these particular instances of them and then use induction to generalize them, these are just brute facts about the world. We can't observe any inner nature of gravity or of motion to explain why motion obeys these three laws or why gravity obeys its inverse square law. This is just the way the world is. And there's nothing else to say. There's just brute facts. There's certain ways the world works. We can discover the way the world works, but then that's just the way it is. That's where it ends. Another interpretation of Newton, though, is it's not that it's a brute fact, but it's just a limit of our knowledge. So on this interpretation of Newton, maybe there is some deeper explanation for why gravity behaves the way it does. We can maybe even formulate hypotheses about the physical or metaphysical nature of gravitational forces, about space, about physical objects, that, if they were true, would explain why gravity behaves the way it does. But perhaps Newton's claim is that even if there is this deeper explanation, we cannot know what that explanation is. We cannot know which of those competing hypotheses are true unless we can make observations of the relevant phenomena, unless we can make experiments that would let us get at that phenomena, get at that nature. And until we can do that, he says, we just shouldn't make any claims about it. It should be enough that we can make these predictions about how objects will behave. We don't need anything else. All right, so that's all for this video. See y'all next time. Bye-bye.